So we're going to be applying the fundamental theorem of calculus to particle motion today. So when we think about the fundamental theorem of calculus, if we took the definite integral from a to b of v of t dt, that means we take the antiderivative of velocity. Now some things to remember here. In this p of t position at time, if I take the derivative of position, so this way taking derivative, the derivative of position, the change in position over time, is velocity. So that makes sense that the antiderivative of velocity would be position. Just to remind you, if you took the velocity derivative of velocity, you would get acceleration. So going backwards, the antiderivative of acceleration would give you velocity. Okay, so go back to this. If we took the definite integral from a to b, that's going to be our position at the end minus the position at the end. Well, doesn't that make sense? That's going to give me my net distance. If we took the absolute value of velocity, that wouldn't be the net distance or displacement. It would actually be the total distance traveled, you know, what my Fitbit says. All right, so those are things we want to remember. The velocity of a particle that is moving along the x-axis is given by this function. If the position of the particle at 4 is 72, what is its position at time equal 2? Well, we can actually use these ideas to answer this question. What if I found the net distance traveled from 2 to 4? I could figure out how far the particle had gone from time equal 2 to time equal 4 and backtrack to figure out where it started. So I really want to find the distance traveled from 2 to 4 of velocity. Now remember, that's going to give me my position at the end minus the position at the end. Well, let's see how that helps us. Okay, so the definite integral from 2 to 4 of 3t squared plus 6. Well, let's see. Antiderivative. I'm going to add 1 to the exponent. It's going to be t cubed divided by 3 plus 6t. And I'm going to evaluate that from 4 to 2. So 4 cubed plus 6 times 4 minus 2 cubed plus 6 times 2. That's going to be my total distance traveled from time 2 to time 4. Well, let's see. That's 64 plus 24 minus 8 plus 12. Let's see, that's 88 minus 20. Total distance of 68. Okay, so I've traveled a total distance of 68. Let me rewrite some of this. So from 2 to 4, v of t, that's going to really give me that change in position from the end to the beginning. So this was 68. P of 4 is 72 minus my position at time 2. Well, what's my position at time 2? Well, it would be 4. What is the total distance the particle travels on the interval from 0 to 7? So let's think about this. 3t squared plus 6. Is that ever going to equal 0? Are we going to ever have negative velocity? No. There is not anything other than an imaginary number that would give me a time of 0. So I don't have to worry about having negative velocity. So I won't have a negative area at all. So if I don't have to worry about any negatives, I can just take that total distance. That was t cubed plus 6t, evaluated from 7 to 0. 7 cubed plus 6 times 7. Whoops. I can use the calculator, right? Is 385. Let's double check it. Now let's remember how we can double check it. Alpha window, I can take the integral from 0 to 7, absolute value of 3, and we'll use x, plus 6. 385. So we were correct in assuming that there was no negative area. Remember, that's the total distance. So, the velocity of a particle is given by this function. Now, this is a calculator bound problem. I'll go ahead and tell you that. Usually I try to put a little calculator symbol. So, the position at t equals 1.5 is this. What is its position here? We're going to use the same type of idea. We need to find the distance that the particle traveled from 1.5 to 3.5 of 0.5 e to the t, that's a t, minus 2 cubed dt. Ooh, I forgot to put my dt's. Oh, no, I did. Okay. That distance traveled will be the difference in my ending position minus my starting position. So, calculator-based problem. I'm going to go to my integral from 1.5 to 3.5 of 0.5 e to the, and we'll just use x, arrow over, x minus 2 cubed dx. And it says that total distance traveled is 15.919. Well, I know the position at 1.5 is 2.551, and I'm trying to find the position at time 3.5. So, to solve the equation, all I have to do is add 2.551. And you get 18.470 is the position at 3.5. The total distance, always note when it says total, from 1 to 5 is going to be the absolute value of that velocity function. So, I'm going to go ahead and retype it. whoops, I forgot, 1 to 5 of the absolute value of 0.5 e to the x times x minus 2 cubed dx. Now, most of these problems, especially with this kind of function, will be in the calculator portion, and they don't mind you using the calculator to calculate, as long as you make sure you're showing your lower boundary, upper boundary, and what you're taking, what's in the function that's in the definite interval. So we reviewed doing it using our new skills of anti-differentiation and using the calculator. The next one's going to be with a graph. The graph of the velocity measured in feet per second of a particle moving along the x-axis is pictured here. The position of the particle at 8 is 12. So P of 8 is 12. Use the graph to answer the following questions. What is the position at 3? So we're trying to find P of 3. Well, I know that if I take the integral from 3 to 8 of velocity, I'm going to find the difference in my ending position minus my beginning position. That could help. 3 to 8. So I'm going to go ahead and divide it up into rectangles and triangles. 1 by 5. 5 times 2 is 10. Half of that is 5. 2 by 2. It's going to be 2. Now remember, that's negative. So 10 minus 2 is 8. So it's a total of 8 units traveled from time 3 to time 8. We know P of 8 is 12, and we're trying to find out where we started at, where we were at 3. Gosh, that's easy. 8 equals 12 minus something. P of 3 is 4. What is the acceleration at 5? Well, acceleration at 5 would be the derivative of velocity at 5. We're not given the formula, but derivative finds, the slope of the tangent line. So what is the slope at 5? Well, we went down 5 over 2. What is the net distance? Net. That means displacement. From 0 to 10. All right, let's see. So that would be a 5. That would be a 5. That would be a 2. 5, 10, 15, 20. 20 minus 4 is 16 feet. Oh, I forgot to put my units here, didn't I? So velocity was feet per second, so this is going to be feet per second squared. Forgot my units. Bad teacher. All right, total distance. Remember the difference between total. We're going to find the integral of the absolute value of velocity. In other words, we're going to make everything positive. So we're going to take the 20 that was positive area plus the 4 and get 24 feet total traveled from 0 to 10. The next one we're going to do is we're going to review the Riemann sums. Now I got to do a little bit more of a review with second block than I did with fourth block, so this is needed. Okay, so this table shows the values of velocity v of t in meters per second of a particle along the x-axis. What does the value definite integral 0 to 18 of v of t with respect to t represent? Okay, so it doesn't have the absolute value. This is, you could say, the net distance traveled, or the displacement from time 0 to time 18. Or you could say in the first 18 seconds. Using a left Riemann sum of 6 subintervals of equal length, estimate the value. Okay, so 6 rectangles, and it's a left Riemann sum. So let's see. 1, 2, 3, 4, 5, 6. So we're going to have these rectangles. And if we're doing a left Riemann sum, that means I'm going to be taking the height that's on the left of each of these. So left Riemann sum means that we're going to use the width this way. So this would be a 3, 3. Oh, they're all the nice same width, aren't they? And the height of the rectangle would be left. So the first one would be 2.3 times 3 wide. The next one would be height is on the left side, 2.73 wide, and so forth. So 2.0 times 3 wide, plus 1.3 times 3 wide, plus 1.0 times 3 wide, plus 1.7 times 3 wide. We have 6 rectangles. And it says to make sure that we use our unit of measure. So this is 33 what? Meters traveled. Right Riemann sum. Okay, so it says to keep using 6 subintervals. So we're still going to have 6 rectangles, all with a width of 3. But instead of using the left number for our height, we're going to use the right number. So right side of each. So it's going to be 2.7 times 3. Plus 2.0 times 3, plus 1.3 times 3, plus 1.0 times 3, plus 1.7 times 3, plus 2.1 times 3. And I got 32.4 meters traveled. The next problem says using a midpoint with 3 subintervals. Okay, so I'm going to go back. Now I'm wishing I had done those rectangles with my erasable pen. So 3 subintervals this time means I'll just do it up here. So I'm going to have a rectangle going from here to here, here to here, there to there. Instead of using the left number or the right number, we're going to use the middle number for our height. So these are 6 wide and 2.7 tall. So the first one was 6 wide and 2.7 tall. The next one is 6 wide, 1.3 tall. The next one's going to be 6 wide, 1.7 tall. And we get 34.2 meters traveled. Using a trapezoidal sum with 6 intervals. Whew, trapezoidal. Okay. Trapezoidal means instead of using the left measure or the right measure of each, we're going to find the average of the 2 heights for each of these 6 rectangles. So, each of them are 3 wide, but instead of choosing 2.3 as my height or 2.7 as the height, I'm going to average the 2. So, I would have 2.3 plus 2.7 divided by 2 times the width of the rectangle of 3, and so forth. So the next one will be 2.7 plus 2.0 divided by 2 plus 2.0 plus 1.3 divided by 2 plus 1.3 plus 1.0 divided by 2, because I'm getting the average of those, times 3, plus 1.0 plus 1.7, averaging, times the width, plus average of 1.7 and 2.1 times the width. So they don't want to see all your arithmetic. That can be done in the calculator. And I end up getting 34.2 meters traveled. So both of these were pretty good. Now the last one says find the average acceleration. Well, I can't find acceleration. I don't have a... Oh, what if we found the velocity at 9 minus the velocity at 3 divided by the change in time. Change in velocity or change in time. We can do that. The velocity at 9 was 1.3. Velocity at 3 is 2.7 divided by the change in time, which is 6. Oops. So let me show you what I did in the calculator. So, whoops, if we do it as a fraction over 6, gives me this long decimal, which is okay, but sometimes we'd rather have it as a fraction. I can write it both ways. That'd be negative 7 over 30, which is approximately negative 0.233. So where in the table would we have this? Where in the table is this average acceleration approximately equal to v prime? Okay, so v prime means instead of us finding the slope of a secant line, we're finding the slope of the tangent line. It's instantaneous velocity. So where would the change be approximately equal to that? So think logically, where would that be closest to the slope of the tangent line? We're finding the average from 3 to 9, so the instantaneous velocity at 6 would be approximately the same as that average velocity at 6. Because if we average, we're getting the average around 6, that's going to be the closest one. Now, we're going to be working some of these problems out in class that are following these AP free response questions. So for those who are going to be absent, I'll record a video on those later. But for now, you're good for class.